Okay. So we are reviewing with logarithms and what you will need to know actually as we're going through calculus. So I'm not just reviewing these because I want to. I like logarithms, but I'm not just reviewing them for no reason. So you will need to know as we go through different calculus problems how to work with laws of logarithms. And then you will also need to know, or it's helpful to know, how to solve equations that involve logarithms or exponents, so that if you do have to solve something like that by hand to get an exact answer, you know how to do that. So I first have up here, just because we talked about inverse functions yesterday, and the reason why inverse functions and then logarithmic functions are covered in the same section is because logarithms are the inverses of exponential functions. We've talked about that already also. So I know I have on here, you know the answer is going to be yes, but I have, does the exponential function f of x equals a to the x for a values greater than 0 and not equal to 1? Does an exponential function have an inverse? And then justify your reasoning. So we know it has an inverse, and that's the logarithmic function. But what property did we talk about yesterday that says a function has an inverse? So horizontal line test tells you you have what? What type of function? A one-to-one function. So all exponential functions are one-to-one. So I could say yes, because f of x equals a to the x is a one-to-one function. And that's true if the a value is greater than 1. It's also true if the a value is between 0 and 1. Greater than 1 gives us the increasing function. Between 0 and 1 gives us the decreasing. The inverse, though, we work with values of a that are greater than 1. So the logarithmic function that we work with will have a base that's greater than 1. So we work with the increasing exponential function. And we had then talked about how inverses, their graphs reflect over the line y equals x. So we know this is the graph of the logarithmic function log base a of x. I could draw in y equals x to show that there are reflections over that line as best I could sketch it there. So then I have on here, we call this the logarithmic function with base a. This is how it's notated, log, and then you see the base a there. So for an exponential function, if it's in the form y equals a to the x, we talked about yesterday how with inverses, you switch the x and the y. So the inverse would be equivalent to x equals a to the y, but we can write that as a logarithm, and this exponential form is equivalent to log base a of x is equal to y. So these are the forms here that are equivalent. And then as a reminder, and I have this as a note below, but Mrs. Holbrook probably had mentioned this to you as well, or maybe even stressed it. So for x values greater than 0, log base a of x is the exponent to which the base a must be raised to give x. So log base a of x is equal to y. In the equivalent exponential form, y is the exponent. So a logarithm represents an exponent. Yes. And then I did give an example. So I have here log base 10 of 0.001 is equal to -3 because -3 is the power you have to raise the base 10 to get 0.001 is the answer. So to go from that logarithmic form to an exponential form, What's nice is in both forms, your base number is the same. So log base 10, 10 is the base of the exponential form. What the logarithm is equal to is the exponent, and then the value in the logarithm is what you get as the answer to that exponential problem. So to go from a logarithm to an exponent, base 10 raised to the -3 equals the 0.001. So I have on here, and this is just some practice. I wouldn't say this comes up a lot on AP tests where you aren't allowed a calculator and they ask you to find a value of a logarithm, but knowing this can be helpful as we work with logarithms. So log base 2 of 8. To figure this out, I could just set this equal to, I could say this equals y. So if I wanted to set this up as an exponential equation to figure out what it's equal to, I would have 2 to the power of y should equal 8. So I'm trying to figure out what power do I raise 2 to get 8. So then this log would equal what? 3. And I had just put the y in there myself. But so log base 2 of 8 is 3 because 2 to the third power is 8. So then part B, log base 3 of 81, you raise 3 to the fourth power to get 81. Okay, then I included the cancellation equations, so the relationship between exponential functions and logarithmic functions canceling each other out since they're inverses, as well as laws of logs, which yes, you need to know those 3 laws of logarithms. So when you have an exponential function, a to the x, and then its inverse, log base a of x. So just like we talked about yesterday, a function and its inverse composed with one another cancel each other out. So if I take f inverse of f, that would look like I'm substituting an exponential function into a logarithm, both with base a. Log base a of a to the x cancels out and you just have x. And then the opposite of that, if I substitute a logarithm into an exponential function, again, bases are the same. So a raised to log base a of x, those also cancel each other out to just get x. And these are the really the cancellation equations you use when you're solving equations that involve logarithms or exponents. Yes, that stuff. You need to know that stuff. So laws of logs. So if x and y are positive numbers, then these, like I said, you need to make sure you know. So if you have log base a of x times y, so the log of a product is equal to the sum of 2 logs. So log base a of x plus log base a of y. Or you could also do the reverse. The sum of 2 logs with the same base, you could write as 1 logarithm, it's the product. Log base a of a quotient, x divided by y, is the difference of 2 logs. Log base a of x minus log base a of y. And then log base a of a power of x to the r, you can bring that power down in front as then a coefficient for the logarithm, or a constant multiplied by the logarithm, so r times log base a of x. As long as you're only raising what's inside of the logarithm to a power and you're not raising the logarithm itself to a power, that would be different. But the parentheses would be placed differently too. So I have, for example, to use laws of logs to evaluate each expression. So rewrite using laws of logs. So for a, if I have log base 2 of 80 minus log base 2 of 5, how could I rewrite this as 1 log? So yeah, log base 2 of the 16 is coming from 80 divided by 5, which would be log base 2 of 16, which then, what is log base 2 of 16? 4. You raise 2 to the 4th power to get 16. We just did math, yeah. What about log? Well, what if you see something like this, log of 50, log of 2, what is the base? 10. Yeah, so when you just see log, this is called the common log, so that means log base 10. They won't ever write, or they don't usually write the 10 in, it's just commonly known that it's the common log, it's base 10. So log of 50 plus log of 2, so I'm adding two logarithms, I can write this as log of 50 times 2, multiply the 50 and 2, so log of 100, which is what? 2. So this is log base 10 of 100. You raise 10 to the second power to get 100. 10 squared is 100. Okay, so now we're going to review the natural log because this is the logarithm you will work with the most often. So I did say yesterday, or not yesterday, but on Monday with exponential functions, e is the most common base. The natural base e is most commonly used for exponential and for logarithmic functions. And that gives you the natural logarithm. So log base e of x is written as natural log of x, ln x. Then I included here that natural log of x equals y. I included the equivalent exponential form. So because this is log base e of x, that's what natural log of x is to the y, you have e to the y is equal to x to get the equivalent exponential form that I have written there. The cancellation equations are the same as the ones I included on the front, so are the laws of logarithms. I just wrote the cancellation equations again with base e because you use these the most often. So if you have e to the x and natural log of x, natural log of e to the x, natural log and e cancel out, you just have x. And then e raised to the natural log of x also cancels to just be x. And then I also have on here natural log of e is 1. Why is that? That's where an exponential function would cross the y, so it crosses the x-axis because it's the inverse. Maria, here's a. Yeah. If I write natural log of e as log base e of e, so this is why it's equal to 1e to the first power is e. Now that's true for any base though. Log base a of a is 1. So like log base 2 of 2 is going to be 1. But that's why natural log of e is 1. This comes up in, I'd say, a fair number of problems where you have natural log of e, and it would be in a fair number of problems that you aren't allowed a calculator on. So this is something you're expected to know, that if you see natural log of e, to know that that simplifies to 1. So make sure you understand, well, know that it equals 1, but understand why it equals 1. So then I have some examples of solving equations. And some of these, there's multiple ways you can go about them. There's one way I prefer, it might not be the way you prefer. So for the first one, natural log of x is 5. I'm going to show you what you could do is you could write this in its equivalent exponential form to find x. So because I know natural log of x is log base e of x, I could write this as an exponential equation, and it turns into e to the 5th power is equal to x. Okay, I just solved for x, e to the 5th power power is a decimal, so I could leave it as e to the 5th and then it's an exact answer. That's it. However, I personally would not solve it that way. What I would do when I see an equation like this is I would cancel out the natural log. And that's where you use these up here. So if I want to cancel out natural log, I need to raise it as a power of e. So I would have e to the natural log of x equals e to the 5th power. So I raise both sides as powers of base e. And then on the left side, e and natural log cancel out, you just have x. And then I still have e to the 5th here. Okay, two different ways for that one to get to that same answer. I would prefer the second way that I just showed you. So then if you look at b, e to the 5 minus 3x equals 10. So this is an exponential equation. I would look at this and say if I'm trying to find x, it's in the exponent. I don't want it to be in the exponent. How do I cancel out e? Well, yeah, you could write it in a logarithm form, or you could cancel it out like up here, taking the natural log of it to cancel it out. So if I take the natural log of both sides, I have natural log of e to the 5 minus 3x equals natural log of 10. The natural log and e cancel, and now my power is no longer a power. It's just brought down. I have 5 minus 3x. But I still have natural log of 10 on the other side. So here I'm showing you exact answers. If I type that in a calculator, I'm going to get a decimal approximation. Chances are you're solving an equation like this without a calculator, so you're going to leave it in exact form. And then to solve for x, I would subtract 5, so negative 3x equals natural log, I'll keep parentheses around the 10. Natural log of 10 minus 5. And then divide by negative 3, so x is equal to natural log of 10 minus 5 all over negative 3, or I could write the negative in front of the fraction if I didn't want to write it in the denominator with the 3. So I could say negative or opposite of natural log of 10 minus 5 all over 3. You could write it that way. You are. If it was a multiple choice question, they probably wouldn't. They'd probably write it like this. So as long as you know, like if that's what you got, that this is equivalent. But if it was free response, you're allowed to leave it there. Yeah. Because simplifying isn't calculus, so they don't give you points. They would only take them away if you did something wrong with algebra. And then I included for C and D. These are ones where the logarithm or the exponent, they're not alone. So make sure before, because I see this is a common mistake, before you raise both sides as a power of e, or before you take natural log of both sides, you need to get the logarithm or exponent by itself first. So I would have to, for this one, I'd have to get natural log of x alone. So I'd have to add 6 and divide by 5. So natural log of x is 6/5. Then I can raise both sides as powers of e. So I would have x equals e to the 6/5. Which, so that's the exact answer. That's fine. What's an equivalent way I could write this, though, so I don't have a rational exponent? Just in case it was multiple choice and you didn't see this as an answer. Yep, 5th root of e to the 6th. That would be the same thing. So again, I know I'm going to say this all year and I'm going to keep repeating myself. Simplifying is not required, but multiple choice will be simplified. And you have to know what or how to simplify something to get it to match, or what forms are equivalent to one another, so you know which answer is correct. And then same thing for D. What I see happen is students would right away take natural log of both sides, and you can't do that because of the 3. This gets, you need to get this by itself first. Divide by 3 first, so e to the x minus 4 equals 4, and then take the natural log of both sides. So natural log of e cancels. I have x minus 4 equals natural log of 4. Add 4, so x is natural log of 4 plus 4. And this first 4 is in the natural log, the plus 4 is not, so don't call that the natural log of 8. Okay, last example on this side, and then I'm going to talk about change of base, which a lot of you with your calculators probably won't even need to know how to do. So it says express natural log of a plus 1/2 natural log of b as a single logarithm. So you want to write this just as the natural log of one quantity. Using properties or the laws of logs. So how could I rewrite this? Okay, I heard some different things. So before I can write it as 1, what can I do with this 1/2? It becomes the exponent on the b, so natural log of a plus natural log of b to the 1/2. Or you can write this as the square root of b. So you could have natural log of a plus natural log of the square root of b. And then if they're added, they're multiplied. So natural log of a times the square root of b. Or if you left it as natural log of a times b to the 1/2, that's fine.
Which one would be the more?
You'd probably see this one. You'd probably see the square root. All right, are there any questions so far on the laws of logs, on the equations? And I know I've been stressing the practice, the homework, the assignment. Make sure you're looking at those problems because they're not all exactly like these, and different things might come up. Even with algebra, different things may come up that we didn't maybe cover or review in class, and that's where you would review that and ask questions. So make sure you're looking at those. But I do have on here the change of base formula. And this you may not even need to use. I'm going to show you, and some of you may have already played around with this on your calculators. I need to get mine out. Because now graphing calculators have it built in where you don't even need to use the change of base formula. You could just type this in if you don't have base 10 or base E. So scientific calculators, and this is how calculators used to be. The logarithm options you had were either log base 10 or log base E, natural log, and that was it. So if you needed log base 8 of 5, you wouldn't be able to just type that in. You'd have to use the change of base formula, which would have been, excuse my pen. So you can either do natural log of x over natural log of a, or log base 10 of x over log base 10 of a. You get the same answer either way. So I would have had to write this as, I'll use natural log of 5 divided by natural log of 8 to get my answer. And then I would type that in because my calculator would allow it. However, and you can check this on your calculators, especially if you have an 84, you are probably allowed to do this. I'm not sure about the 83s. Inspires probably can do it. I'm not as familiar with those. On the graphing calculator, if you go to, I think I found this under math, the math key, and you actually go down to, it's A. So it says log base. And if you click enter, then you type in the base and the number. So log base 8 of 5. Yeah, so 83s might not have it, so 83s you would have to use the change of base formula then. Now, this doesn't come up a lot though, like where you have to give that as an answer. It's not a common thing, but just so you know how to do it. Okay. No. So yeah, natural log of 5 divided by natural log of 8, or log base, or log of 5 log of 8 divided, you get the same answer. Oh, that's nice. Okay, and then the last thing, in the past, I've kind of looked at the time and skipped over this example, and then there's just been questions, so I'm not going to skip over it. So, what I have in here in lesson 1.5, I need your attention, please. This is getting relating with inverses. So in lesson 1.5, we had a problem that dealt with strontium 90, and we said the mass that remains from a 24 milligram sample after T years, we had come up with this formula. So 24 times 1/2 to the T divided by 25. The half-life was 20, or the half-life was 25 years. This says find the inverse of the function and interpret it. So I'm gonna, I know I have m equals f of t. I'm gonna keep it as m. So we have m equals 24 times 1/2 to the t over 25. When you have a function where your variables aren't just x and y, and they represent specific quantities, like m represents mass, t represents time, you do not want to change the variables. You don't want to switch them. Because if you switch them, now you're saying m represents time and t represents mass, and that just doesn't really make sense. So don't switch the variables if they mean or represent specific quantities. Leave them where they are. You just solve for the other variable. So to find the inverse, I would solve this for t. Okay, what do I have to do to this equation first to solve for t? T is in the exponent. I'd have to divide by 24. So m divided by 24 would equal 1/2 to the t over 25. How do I get t out of the exponent?
No.
You could write it, yeah, that would be an equivalent form, like this would be the 25th root of 1/2 to the power of t. That would be an equivalent form. So I'm going to show you how you can do this. There's actually different things you could do here. Here we also had an x in the exponent. We took natural logs of both sides. Yes, it canceled out the e. Even though I do not have base e, I can still take the natural log of both sides. It is not going to cancel out the 1/2, but by laws of logs, it allows me to bring this down in front. And now it's no longer an exponent. So I'd have natural log of m divided by 24 equals t over 25 times the natural log of 1/2. Now I could have used log of any base. I could have used log base 10 if I wanted to. I just chose natural log because we use it most often. And now from here, I would have to multiply by 25 and then divide by natural log of 1/2. So if I multiply by 25, so 25 natural log of m over 24 equals t times the natural log of 1/2, and then divide by natural log of 1/2. So t will equal 25 natural log of m over 24 all over natural log of 1/2. So you can't do anything to combine those logs. When you have the quotient of 2 logs, you cannot rewrite that in a different form. You might see natural log of 1/2. This I can rewrite. I have the natural log of a quotient. I could write this as natural log of 1 minus natural log of 2. What is the natural log of 1? Not e, 0. The reason why log base e of 1, e to the 0 power is 1. That's why it's 0. So you might see natural log of 1/2. Like if you're checking answers in the book, might be written as the opposite of the natural log of 2. And that's why. So you could put that in place of it here. However, this is an acceptable answer. And then for interpreting, we didn't talk too much about interpreting inverses. So the original function was a function. It was showing the mass remaining after t years. What is the inverse showing? Because this is really, t is now a function of m. So it's representing the time it takes to reach a certain mass. So you might have a question where it says, how long will it take for the first strontium-90 to decay to 2 milligrams? So you substitute in 2 for m now into this equation and find the time. So make sure you understand how to find an inverse and then interpret it if they do give you specific quantities. Okay, so I know, sorry we ran out of time, we don't have work time, but look at that practice. I think going through those examples will hopefully help.